I am a biochemist by training, but I study fungi. I'm interested in how they grow, how they modify their cell wall during growth and metabolism, and looking for some unique proteins that are involved so that maybe someday I can make an antifungal drug to target these nasty bugs. And they're not all nasty. Some of them give us good things like cheese and beer and wine, but sometimes they cause disease. So finding proteins involved in cell wall metabolism is what I do in my laboratory, and I involve many students during the semester and the summer. I was always interested in science since I was in grade school. But I went to college and I wanted to pursue other things because I knew somewhat about science, but there were so many opportunities to take courses. So in addition to the science courses I took a lot of social science courses, and we had a major at Clark University called Science, Technology, and Society, which was a bridge between sciences and social sciences, and that's what I majored in. So I did not do a traditional chemistry degree or biology degree or science degree, and I learned a lot, and I loved the bridge between the two disciplines. I have a lot of things I like to do outside of science and outside of teaching. I'm a big country music fan, so I go to Country Music Fest every year, where there are plenty of great performers. It's a fundraiser for music education, so I'm very happy to support this endeavor. I'm an avid Memphis Grizzlies basketball fan, so I go to the games regularly. And you can see that my tennis racket, which has just gotten restrung, I play a lot of tennis, and actually I played competitive tennis in college. I played Division III for Clark University, and we spent a lot of time traveling to matches. And one of the real challenges during my undergraduate education was to balance the athletics with the academics. And I had to learn a lot of time management. I had to learn a lot of discipline, because oftentimes we would leave for a match early afternoon on a van, and you know, on a van you really can't do any work. We'd play our match, we would come back maybe late in the evening, and I would have to find time to do my homework and study for tests. Well, I thought I managed it pretty well in my sophomore year when I was taking organic chemistry. And in the first semester, I got an A. So I was all excited, figured I got this organic chemistry thing down. Now, all of a sudden, second semester comes, and I got a little overconfident, and I did not build in enough time to study for the first exam. And I got a big fat F on the first exam. Not just D, not C, F, and I failed pretty badly. So I figured I had two choices. I could either go home and cry and switch majors and figure science wasn't for me at all, or I could figure out a way how to make the second exam work for me. So I decided I was going to do the latter, and I was going to just have to buckle down, study harder, and find more time in my day to study for organic chemistry too. So the next exam I got an A, and as it turns out the professor dropped the lowest exam, and I managed an A for the course. It was a valuable lesson that I learned, that sometimes you think you can do things and you can't, and you have to figure out ways to make things work for you. There's no specific set of rules or set of things that the professor can help you with. You have to find it within you to manage your time, to manage what your life and what's important to you, and get it to work. Hello students, today we're going to learn about aqueous solutions. You're probably wondering why you should care about a solution, what is a solution, and how do we do calculations involving solutions. Solutions are part of our everyday life. Here in Memphis, Tennessee, it's pretty hot, and playing tennis outside or doing any vigorous activity means you're going to sweat a lot. If you sweat significantly over a long period of time, you might become dehydrated. If you dehydrate significantly, this might lead to a trip to the emergency room. If you do go to the emergency room, they will give you an IV solution, and it's a bag of stuff. In the bag of stuff, we have sodium ions, chloride ions, and a carbohydrate called glucose, also sometimes known as dextrose. All of this is in water. They administer this in your veins to help you rehydrate. So this IV solution, which is good for rehydration, is a solution that has a lot of components in it. And when we talk about solutions, we're going to use two basic terms. First, we're going to talk about the solute. The solute is present in the smallest amount. We also have the solvent, which is present in larger amounts. So in our IV solution, the sodium, chloride, and glucose are known as the solutes. The water is the solvent. Although we know the components in an IV solution consist of sodium ions, chloride ions, and glucose, it's not enough just to say that they exist in a solution. We want to know how much of each is in a solution. So we have to talk about their concentration. So when we talk about concentration, we typically use the term molarity, or big M, equals the moles of solute divided by liters of solution. So we want to know the molarity of sodium chloride and the molarity of glucose in 100 milliliters of solution. So per 100 milliliters, what's the molarity? For glucose, we have 5 grams of glucose. We can convert the grams to moles using the molar mass, and we would come up with 0.028 moles of glucose. We can do the same for sodium chloride, 0.90 grams times 1 mole of sodium chloride gives me, there's 58.44 grams per mole, and that is equal to 0.015 moles. In an IV solution, per every 100 milliliters, there are 0.028 moles of glucose, 0.015 moles of sodium chloride. To find the molarity from the moles, we have 0.028 moles of glucose. If we have per 100 milliliters, we have to divide then by liters, which is 0.10 liters, 0.10 liters, and we come up with 0.28 molar glucose and 0.15 molar sodium chloride. So, in an IV solution, you have 0.28 molar glucose, 0.15 molar sodium chloride. Let's just say theoretically you can go and make an IV solution. So I want to make 2.5 liters of an IV solution. Well, I know I have 0.28 molar glucose and 0.15 molar sodium chloride. So I would take the molarity times the volume, so 0.28 moles per liter times 2.5 liters times the molar mass, 180.2 grams per mole, and I would come up with the number of grams, which is 126 grams. If we're mindful of significant figures, about 130 grams of glucose. If I want to find how much sodium chloride, 1.5 moles per liter of sodium chloride times 2.5 liters times the molar mass, 1 mole, 58.44 grams, and I would come up with 22 grams. So if I wanted to make my own IV solution, I would have to find a big beaker, put some water in it, add the 22 grams of sodium chloride, add the 130 grams of glucose, and bring the volume up to 2.5 liters. So technically, or theoretically, I can make an IV solution, and when we have the molarity and we know the volume, we could figure out how many grams we need to make the solution. Another important piece when we think about concentrations of solutions is an important process called dilutions. Dilution is the lowering of the concentration. So here we have a beaker, and it might have something like sodium chloride in it. And here we have a beaker of sodium chloride. So we have sodium and chloride ions in the solution. If we dilute it, that we're adding volume to the solution so that the number of particles of sodium chloride is at a lower concentration. Why do we care about dilutions? Dilutions are an important part of working in a laboratory. And even though some of you may not work in a laboratory, it's still an important idea. For example, if you go get a cup of coffee at the local coffee shop and it's too strong, you would add water to it to dilute out the flavor. So dilutions are an important piece of everyday life and certainly an important piece of chemistry. When we do dilutions, there's a very useful equation we can use. Molarity initial times volume initial equals molarity final times volume final. So M times V initial equals M times V final. So let's go ahead and see how we can use this equation to help us with dilution problems. So I've given you an example here. The concentration of sodium ions in seawater is higher than in human cells, which in human cells it's about 12 millimolar. How much water must be added to 1.5 mils of seawater to make the sodium concentration equal to that in cells? Let's begin the calculation. So using our equation, M1V1 equals M2V2, we can find the answer to this question. First, we have to convert 12 millimolar to molar. So 12 millimolar is 0.012 molar. 1.5 milliliters is 0.0015 liters. So plugging these numbers into our equation, we know that seawater is 0.481 molar in sodium ions. We have 1.5 milliliters or 0.0015 liters. In the cells, we have 12 millimolar or 0.012 molar. When we do the math, we find the volume is equal to 60.1 milliliters. So So how much water do we need to add? The total volume needs to be 60.1, so we need to subtract 1.5 milliliters, and we come up with 58.6 milliliters of water needs to be added. So using this equation, we can solve the problem. So we need 58.6 milliliters of water to add to the solution, to add to the 1.5 mils of 0.481 molar to achieve the 12 millimolar concentration of sodium ions in human cells. So this is how we do dilution problems with this equation.